Hydroboration-oxidation is an alkene addition reaction. This is a two-step reaction, very much like oxymercuration, demercuration. In the first step of this reaction, we will react our alkene with a reagent called borane. There are two different ways that we can commonly see borane written as a reagent. One method, the way that I just wrote, is BH3, and this is a dot, THF. The other method, so let's go down here, BH3.THF. The other way that this could be written is B2H6. And so both of those notations mean the same thing, and again, this is called borane. THF is a solvent, tetrahydrofuran. It's a very common solvent. And when BH3 is put into THF, it forms a complex with THF, which is what this dot represents. It doesn't react, so it doesn't make an entirely new molecule, so we don't write it as one molecular formula, but it is more than just being simply dissolved into BH3. So that's kind of a side explanation of that notation. The step one is BH3 in THF or borane, and step two is hydrogen peroxide, H2O2, in a basic solution of hydroxide, OH-. This reaction adds a hydrogen and an OH group to the carbon-carbon double bond. So this is another way of adding water to an alkene. Let's look at the conditions of this reaction, because this reaction is actually kind of unique in terms of its conditions. So first of all, number one, this is an anti-Markovnikov reaction. The only other time we've seen an anti-Markovnikov reaction that also used H2O2. So you should be kind of getting the idea that H2O2 is going to be associated with anti-Markovnikov addition. Second condition is that there is no rearrangement to the carbon skeleton. There is no carbocation formed in this reaction, so we have no rearrangement. And then the last condition, and this is a new one, is that we have something called syn addition of the hydrogen and the OH. Syn addition means that the hydrogen and the OH go to the same side. It's kind of like cis, same side of the double bond. And ultimately, what it means is that they will both have the same stereochemistry in the product of the reaction. So for example, the hydrogen and the OH will both be on wedges, or they will both be on dashes. Let's take a look at how this works with a couple of examples, especially because we have this new idea of syn addition. So here are two examples for us to practice with. Since there's no rearrangement of the carbon skeleton, let's start by drawing our carbon skeleton. And let's focus on the two carbons that we are actually going to be working on in this reaction. So we know from this reaction that we're going to be adding a hydrogen to one of these carbons and an OH to the other. And we're going to do this anti-Markovnikov, which means in terms of Markovnikov, Markovnikov means that the hydrogen would go to the carbon that already has the most hydrogen. So the hydrogen would go here if it was Markovnikov. That means that we want the hydrogen to go over here. So let's put the hydrogen on this carbon right here. And that would mean that our OH group goes on this carbon right here. So how can we communicate the syn addition aspect of this reaction? There's a couple of different ways that this can be done, but for me personally, the easiest way to draw syn addition is to go back to the original alkene, to pick the two substituents that are cis to each other. In this case, it's two ethyl groups, and give those two substituents identical stereochemistry, because we know those substituents are on the same side of the double bond. And then take the other two substituents that are cis to each other, so a methyl group and a hydrogen, and we're going to give those substituents identical stereochemistry as well. So we'll give those a dash methyl and a dash hydrogen. So I'm going to actually draw it over here as well, so you can kind of see how this is working. A dash methyl and a dash hydrogen. And then what I do is draw one version of the product, like this one here, where the hydrogen and the OH group are both sticking down, so they are syn, they're on the same side. And I'm going to redraw. So you'll notice that I'm not changing anything about wedges and dashes. Redraw the molecule, CH3, and I'm going to draw a second product where the hydrogen and the OH are on the other side of the double bond. So one where they're both down and one where they're both up. This seems kind of tedious, but this is actually the most foolproof way of correctly drawing the stereochemistry of these reactions. Let's practice it again down here with this molecule, with our next molecule. And actually I'm going to make this molecule a little bit more complicated, because the way that it's drawn, it's just kind of overly simple. So let's put a couple more substituents on this guy. Okay, so start by drawing your carbon skeleton, but getting rid of the carbon-carbon double bond, and focus on the carbons that you're going to work on. Now, we know we're going to be making two products, so why don't we just draw both of those carbon skeletons just right now. Now, we know also that our H and our OH are going to be added syn. So let's draw one product where the H and the OH are sticking down and one where they're sticking up. So here's our double bond. Here's the carbons that we were working on. Let's draw one product where they're both sticking down, so they're going to be here, and one product where they're both sticking up, here and here. So we're just kind of working on the framework of this. Let's figure out what goes where. So we're going to add an H and an OH, and what should go where. According to Markovnikov's rule, the hydrogen that we add would go here if this was a Markovnikov addition, but it's not. So that means we're going to be putting the hydrogen out here on this carbon. So we can fill that in. Hydrogen goes here, and the OH goes here. And same for our other product, anti-Markovnikov, just like that. And last but not least, let's fill in our stereochemistry. So we're going to pick two things that are on the same side of the double bond. And we're going to, let's say we make both of those wedges. We could make them both wedges, or we could make them both dashes. We'll make them both wedges. And then we pick two things that are on the other side of the double bond, and we will make both of those dashes. Just like that. And, you know, in terms of the order in which I did all these different things with the products, it doesn't really matter. Maybe you want to start by putting the wedges and dashes in first, and then you add your H's and your OH's. You could really do these things in any order. You're going to end up with the correct product. And again, I know that this might seem a little bit on the tedious side, but this, like I said, this is the most foolproof method for getting your products with the correct stereochemistry.